In the last video, we introduced some basic 2D kinematics puzzles. In this video, we'll look at projectile motion where an object has an initial vertical velocity. We'll start by revisiting a puzzle from a few videos ago, the one where a child dropped a ball from a rising hot air balloon. But we'll change it slightly. The hot air balloon will still rise at 5 meters per second. But this time, when the balloon reaches a height of 30 meters, a child in the basket will throw the ball horizontally at 10 meters per second. Where does the ball land? As we solve this problem, compare the way that we solve it to the way that we solved the earlier hot air balloon puzzle. You'll see not only that 2D kinematics is largely just 1D kinematics solved twice, but also that projectile motion, that is 2D kinematics under gravity, is basically the same as freefall with an additional motion in the x direction nailed on. We start, as usual, by drawing a picture. I will set photo 1 as the point where the ball was launched, and photo 2 as the point where it lands. I will set downwards as positive y and rightwards as positive x. We are being asked for how far the ball travels horizontally. We're asking for the distance that it travels as it falls. So that would be the displacement in x. That's our unknown. What is known over here? Well, we know that the ball is going to fall by 30 meters. So that means that its displacement in y will be 30. Its initial velocity in x is 10 because it was thrown at 10 meters per second. The initial velocity in y will be -5 because that's the speed with which the balloon was rising. The acceleration is 0 in x, and it is positive 9.81 in y. So here's what we have to do. We are given 3 pieces of information in y and only 2 in x. So we cannot yet solve the toolbox equations in x. We can only do it in y. So let's say we solve the toolbox equations in y and we find out the time. Then we use the time alongside the acceleration and the velocity in x to find the displacement in x. Let's go ahead and do this. So in the y direction, we know the displacement, the initial velocity, the acceleration, and we're looking for the time. There is only one equation that weaves together these 4 quantities. Delta y is equal to v initial times t plus half a t squared. That's right, toolbox equation number 2. So let's plug in everything we know. And then let's simplify somewhat. Half of 9.81 is 4.905, and I'm going to flip the order of these 2 terms so that we can put it into standard form. Then comes the minus 5t. The 30 can come over to the other side, which means we subtract it from both sides, which means this becomes a negative 30. And the whole thing is equal to 0. Okay, we now have a quadratic equation. So let's apply the quadratic formula. And then substitute everything in. B is -5 plus or minus square root of b squared minus 4a is 4.905 times c, -30, all divided by 2 times a, which was 4.905. Let's start simplifying this. Negative 5 becomes positive 5, plus or minus the square root of, this I'm going to use my calculator for. Negative 5 squared minus 4 times 4.905 times negative 30 gives us 613.6. We need to take the square root of 613.6, 24.77. Now, this being time has to be positive. So I'm not going to bother with 5 minus 24.77. That's going to give me a negative answer. So I'll only take a look at the positive one. So 5 plus 24.77 is equal to 29.77. That gets divided by 9.81. .03. So the time is 3.03 seconds. Now we have 3 pieces of information in x. So we know the time, we know the acceleration, we know initial velocity, and we're looking for displacement. Once again, we use toolbox equation 2. Delta x equals v initial times t plus 1/2 acceleration times t squared. So delta x is equal to v initial, which is 10, times 3.03 seconds, plus 1/2 acceleration, 0, and time is once again equal to 3.03 seconds, and this whole thing gets squared. But because you're multiplying by an acceleration of 0, this entire term is going to cancel out. So you'll be left with 10 times 3.03, which is 30.3 I hat meters. And now we have solved for how far away the balloon, or rather the ball, will land away from the balloon. Now, let's adapt the cannon puzzle from the last video. A cannon is at the edge of a 15-meter cliff. It fires a cannonball at 40 meters per second at an angle of 45 degrees above the horizontal. Solve for the cannonball's A, time of flight, and B, range. As we solve this, we'll see there's functionally no difference between this puzzle and the hot air balloon puzzle that we started this video with. We begin, as usual, by drawing a picture. I will set the initial position of the cannonball just as it has left the mouth of the cannon as photo 1. And the landing position of the cannonball as photo 2. I'm fully aware this is a very approximate trajectory of a cannonball, but bear with me. This time we will set upwards as being positive y and rightwards as being positive x. Now, let's write down all the information that we know. We know that the cliff, or more correctly, the cannonball, is going to descend a height of 15 meters. So delta y between photo 1 and photo 2 is ultimately going to be negative 15. We know the acceleration in x is, as usual, 0. And the acceleration in y is this time negative 9.81 j hat meters per second squared. So far, so good. But what about the initial velocities? We don't have enough information without those initial velocities to solve. Well, let's look at the initial velocity a little bit more closely. I'm going to draw a close-up of the cannonball just as it gets launched. I will draw in the axes as well. Now let's think for a second about what we were told. We were told that the initial velocity of the cannonball was 40 meters per second at a launch angle of 45 degrees. Velocity is a vector, and what we see here is that this vector has been given in a form that has an angle in it. This is a vector in polar notation. But the toolbox equations use x and y. They use rectangular or Cartesian notation. So whenever you're told an angle, that means that you've been given a vector in polar notation and you need to translate it back into Cartesian before you can start using the toolbox equations. Fortunately, this is exactly what we started the year with. So we are going to do just that in our usual way. I'm going to complete this right triangle. This side over here, the horizontal side, is the x component of v initial, and this side over here is the y component. Now, when we are given a vector in polar, how do we figure out the x component? Like this. The formula is r, that's the length of the vector, multiplied by the cosine of the orientation angle, theta. In this case, that would be 40 times the cosine of 45 degrees. .28. So VI in the x direction is 28.28 I hat meters per second. What about the y direction? Here, the formula is r sine theta. So, r, again, a length of 40, times the sine of theta, which is 45 degrees. .40 sine 45 is the same thing, 28.28. And now we have 3 pieces of information in y, thanks to the fact that we took our original velocity, which was in polar, and translated it into its Cartesian or rectangular equivalent, so we could find the extra information needed for our table. Remember what the question was originally asking for. We needed to find the time of flight and the landing point, or in other words, the displacement. At this point, we have so much information in the y direction that we can easily solve for the time of flight. All we need is an equation that weaves together displacement, initial velocity, acceleration, and time. At this point, as you've probably guessed, this is going to be toolbox equation number 2. So, delta y, negative 15, equals v initial So, we're back to a quadratic equation. Let's simplify this and rewrite it in standard form. Half of negative 9.81 is negative 4.905 plus 28.28. Add 15 to both sides and you get plus 15 is equal to 0. Now, we take this and we plug it into the quadratic formula. Now we need to solve for this square root over here. (28.28) squared minus 4 times negative 4.905 times 15 gives us 1094.05. Now I take the square root of that, is 33.07. Now, negative 28.28 plus 33.07 will give us a positive number, and a positive divided by a negative will give us a negative number. A negative time is not something that is suitable for solving this question, so we're only going to go with the negative root that will produce a positive time. So, negative 28.28 minus this answer, 33.07, gives us negative 61.36. That now gets divided by negative 9.81. So that gives us 6.25 seconds. So that's our time. That is the time that it takes for this cannonball to arc and land in the valley below. The other part of the question was to find the range of the cannonball. Range is just a synonym for displacement in x. And it's very simple to find the displacement in x. We now have 3 pieces of information in x: the time, the acceleration, the initial velocity, and we're looking for the displacement. So toolbox equation number 2 will serve us handily. V initial, 28.28, times a flight time of 6.25, plus half, times acceleration, 0, times t squared. I'm not even going to bother writing t all over again because anything multiplied by 0 is just going to give you 0. So we're left with 28.28 times 6.25. $176.75. So that's our range. That's our displacement in x, 176.75 I hat meters. And one thing which I'm sure you must have noticed is that the basic process that we used to solve this question was identical to how we solved the question about the hot air balloon that we started this entire video with. A variant puzzle is one where the cannon is tilted, usually above the horizontal. In this case, the cannonball will travel upward, reach its peak, and then fall down to the ground. A typical puzzle might read like this. A cannon fires a cannonball at 25 meters per second at an angle of 30 degrees above the horizontal. What is the peak height of the cannonball? As usual, we will start by drawing a picture. We will use two photos, one a nanosecond after the cannonball is fired, and one at the instant it reaches its peak. We will set upwards as positive and rightwards as positive. The velocity of the cannonball at the moment of launch, that is, its initial velocity, was 25 meters per second at an angle of 30 degrees. Now, this quantity contains both a size and a direction, so it is a vector. But the direction was expressed in degrees. This vector is in polar notation. When we solve kinematics puzzles, we always have to do them in Cartesian. So we have to translate the initial velocity from polar to Cartesian. Converting to Cartesian means breaking the vector into two components, the x component and the y component. If the angle in polar is standardized with positive x being 0 degrees, then the horizontal component of the initial velocity is given as size times the cosine of angle, r cos theta. That's 25 times the cos of 30 degrees. The cos of 30 degrees is 0.866, and 25 times 0.866 is 21.65 meters per second. The vertical component of initial velocity is r sine theta. That's 25 times the sine of 30. The sine of 30 degrees is 0.5, and 25 times 0.5 is 12.5. So now we have the initial velocity of the cannonball in Cartesian. It is 21.65 I hat plus 12.5 j hat meters per second. Now we can start building our table of knowns. We now know the x component of velocity, 21.65 I hat meters per second, and the y component, 12.5 j hat meters per second. The accelerations are the same as in the last example, 0 in the x direction and negative 9.81 j hat meters per second squared in the y direction. Negative this time because we set upwards as positive. And there's one final piece of information that is implicit. In 1D kinematics, at the peak of motion, the object has to change direction, which means at the peak, the vertical velocity is 0. We now have three pieces of information in the y direction. We can solve for the peak height using toolbox equation 4. It works out to 7.96 j hat meters. That is, the maximum height of the cannonball is 7.96 meters above its initial height. That's what this puzzle was asking for. But while we're at it, we can also solve for the other quantities. We can use toolbox equation 1 to find the time it takes for the cannonball to reach the peak. .27 seconds. We can use toolbox equation 2 in the x direction to find out how far it travels horizontally when it reaches the peak. 27.59 I hat meters. And finally, we can use toolbox equation 1 in the x direction to find the horizontal velocity at the peak. (21.65 I hat meters per second). Here's another. A cannon is at the edge of a cliff. It fires a cannonball at 40 meters per second at an angle of 10 degrees below the horizontal. The cannonball lands 15 meters away. Solve for the height of the cliff. Once again, we start by drawing a picture. I'm going to set photo 1 as the launch point of the cannonball, and photo 2 as the landing point of the cannonball. I'm going to set upwards as positive y and rightwards as positive x. Just in general, whenever you have tilted cannon questions, it's easier to set upwards as positive and rightwards as positive instead of doing anything unusual with the axes. The reason for this is because if you set upwards and rightwards as positive, it is very easy to translate a vector which is in polar into Cartesian without having to worry about getting the pluses and the minuses, the signs, incorrect. Now, in this case, the unknown is the height of the cliff, the height by which the cannonball falls. But we do know the displacement. The range of the cannonball was 15 meters. So that's the displacement in x. The initial velocity was given to us in polar, so we will have to solve for that. The acceleration is its usual 0 in x, and negative 9.81 in y because we set upwards as being positive. Now, let's zoom in on this cannonball as it gets launched. As it gets launched, it's moving in this direction. That's the direction of its velocity. And indeed, we were told that its velocity was 40 meters per second at an angle of negative 10 degrees. Let's fill in the axes. And now let's start breaking this into its components to convert it from polar into Cartesian. Here's the x component, and there's the y component. The x component, Vix, is always given as r multiplied by the cosine of theta. And the y component, Viy, is always given by r sine theta. So, r cos theta works out to 40 times the cosine of negative 10 degrees. That's 39.39. And V initial in the y direction is going to be r sine theta, which is 40 sine of negative 10 degrees. And that works out to negative 6.95. Now, we notice that in this case, we're looking for the displacement in y, that's the height of the cliff, and equivalently, the displacement vertically of the cannonball. But we have only two pieces of information in y. We need a third piece of information, like, let's say, the time. So, we can solve the x direction for time, because we have three pieces of information in x, find the time, and then use the time to solve for the displacement in y. Let's go ahead and do that. In x, we know displacement, initial velocity, and acceleration, and we're looking for time. Once again, we need toolbox equation number 2 to solve this for us. So, delta x because this entire term has an acceleration of 0, it's of course going to cancel out. So we're left with 15 is equal to 39.39 times t, or dividing both sides by 39.39, we get 15 divided by 39.39, or 0.380 seconds. So that is the time that it takes for the cannonball to land. That's the time of flight of the cannonball. It's the hang time of the cannonball. Now we have three pieces of information in y, so let's go ahead and solve for displacement. So we're looking for displacement in y, and we have v initial, acceleration, and time. This is easily solved using, once again, toolbox equation number 2. So, delta y is unknown, v initial, negative 6.95, times a time of 0.38 seconds, plus half times acceleration, times t squared. So, negative 6.95 times 0.38 is negative 2.64. And 1/2 times negative 9.81 times 0.38 squared equals negative 0.71. So adding these two together, negative 3.35. So this was the vertical displacement of the cannonball, or equivalently, this was the height of the cliff. In this video, we looked at examples of projectile motion where an object has an initial velocity in y. We saw that for some of these puzzles, we need to convert the initial velocity from polar to rectangular before we can apply the toolbox equations. In the next video, we'll see how to solve for an unknown launch velocity and an unknown launch angle. In other words, how to solve for unknown variables in polar.